Good evening, everyone. I am Seung-Bin Kwon, Chair of Quantum and Introductory Seminar Manager of QISCA. It is my pleasure to introduce today's introductory seminar speaker, Hyungmin Lim. Hyungmin is the senior in the School of Electrical and Electronic Engineering at Yonsei University. He is currently the president of QIYA, the Quantum Informatics at Yonsei, and his main interest is quantum error correction. In last winter, Hyungmin gave the talk titled Basics of Superconducting Qubits, and today he will be presenting a talk titled Physical Noise and Control of Superconducting Qubits, sharing insights from a quantum engineer's guide to superconducting qubits. Also, for the presenters, it would be great if you shortly repeat the questions for the audiences. Please welcome Hyungmin Lim to the stage.
Hello everyone, my name is Hyungmin Lim, and I'm the president of KIA, which is Quantum Information Club in Yonsei University. Um, I talk about the basics of superconducting qubits on February post, so I will uh, have a brief review about the superconducting qubits, and additionally, I will explain some type of noises in superconducting qubits and how to control that. So this is online. And first, quantum superconducting circuits. Um, so basically, superconducting is the only artificial atom um, platform in between the various quantum platforms. First, like electron spins in silicon, quantum dots, trapped ions, ultra cold atoms, or nitrogen vacuumness in diamonds, and polarized photons are all natural microscopic quantum systems. So superconducting qubits is a kind of attempt of um, implementation of artificial atoms, quantum microscopic quantum system to macroscopic quantum system. So basically, superconducting qubits uses the superconductivity. So in the superconductor, there are some named Cooper pairs in the superconductor, which is explained in BCS theory. So a superconducting uses these Cooper pairs, charge or flux or other things. So we basically use the physical property of a Cooper pair in superconducting qubits. So that's why we use superconducting in this circuit. So superconductor has three main um, properties: dissipationless and very high Q resonators, phase current Cooper pairs. So, um, why we need the high Q resonators? Because we need to um, we need to conserve the energy in the circuit. So that's the main reason to how to not lose informations in the superconductor qubits. So this is the linear resonance circuit before we learn about the superconducting qubits. So we can see these Hamiltonians in the linear resonance circuit. Um, Basically, we are more friendly to the classical called Hamiltonian, like um, half kx squared plus um, the um, half of mv squared. So that looks like very similar structure in the linear resonance circuit. So we can make this Hamiltonian to the Q about the Q Hamiltonian. So we can find the same structure in the classical mechanics by Q by X. So we can you can see the X to Q, and so other constants to C or L. So basically, the um, in the electrical resonator, V and I are not commutative, like P and X are not commutative. So we can briefly into harmonic to our unharmonic oscillators. We don't use harmonic oscillator in the superconducting qubits because harmonic oscillators have some problems to implement the qubits. So we use this Josephson junction, which is nonlinear inductor. So like these Josephson junction properties make some good properties in the superconducting qubits. Like current is sign phi, which is phi is the flux in this um, junction. So, so we can make some non-linearity in this um, junction. So we can compare the harmonic oscillator and the Josephson junction. So harmonic oscillator has basically same differences in but in the energies. So we can we can see in the zero state to one state and one state to two states or have same difference energies, but we can in the transmon, which is Josephson junction, one to zero to one state is the biggest energy difference, and other energy levels are all different. So we can use unharmonicity to make qubits, not qubits. So we want to use just zero state and one state. So other states can be used in the transmon. So this is good property for superconducting qubits. So there are many design space for superconducting qubits. Like these kind of superconducting qubits are explained like a tunable transmon and flux qubit and fluxonium and Cesian flux qubit and fixed frequency transmon. So I will explain about these transmon qubits later. So we can explain these five models to this one model. So we can model these qubits to just one junction in here and many other junctions in the right side. And also there are capacitor to um, reduce noise. So these are the types of superconducting qubits. So um, actually we used quantum state to charge and flux. So um, these two type of qubits, A and C, are uses the charged qubits, and E and G are flux qubits. So we can find from these graphs the difference of between the transmodes. So symmetric transmode has the symmetric junctions in the circuits, and asymmetric transmodes are have asymmetricity, so we can use more usable transmon in here. So and also C-shunt flux qubits and C-shunt fluxonium also shows the property of the transmons. So we can see the many kinds of qubits in here. So um, there are uses phase qubits or flux qubits or charge qubits. So many kind of property in Josephson junction can be used to quantum states. And I'm going to explain about quantizing of superconducting circuits. So first we can start in the quantum harmonic oscillator. So we can quantize um, this flux property et equals vi dt and phi t is vt dt. So we can make this um, equality from these equations. So we can construct the Lagrangian by this flux. So we can find the structure of Q and phi, the the canonical transformation. So we can find this phi and Q of Poisson bracket is one. So also in quantum, phi and Q are commutator of Q and phi or I bar. So it means we can use phi and Q are equal to the P and X in the quantum mechanics. So also we will talk about the introduction Hamiltonian engineering, because we don't only use the superposition of qubits, we also have to construct the entanglement of qubits. So we will explain about the interaction Hamiltonian because we can make some interaction term between the qubits so it can make entanglement in the superconducting circuits. So there are two kinds of couplings. First one is capacitance coupling. So this is the capacitance term, and second is inductance coupling. So this term is the interaction term in the inductance coupling. So we can physically make some interactions between the superconducting qubits. These two circuits are about the capacitive coupling between the superconducting qubits. So we can make some interaction capacitor between the qubits, and so um, in the these two kind of couplings are about the inductive couplings. So we can use the inductors in the superconducting circuits, and we can basically inductors have mutual inductance, so we can make some interaction terms between the superconducting qubits. So there are some kind of couplings. First one is transverse coupling. So in capacitive inductive coupling makes this kind of transverse coupling. So it can make some energy exchange and change XY phase. So it can make the cubic gate. So and a longitudinal coupling is like coupling resonator, squid, or some different kind of between to the transverse coupling. So you can relate it about the resonance axis and z axis. So you can use in the measure and or error correction. So basically we use z basis measures in the circuits. So we can determine 0 and 1. It's about the z axis. So this is the quantum harmonic oscillator reviews. And also we can quantize some fluxes in these properties. So we can construct some um, Q Q operator and phi operator, and also we can some make some creator or annihilator in this kind of quantum harmonic oscillator. So we can make also uh, the phi operator about the phase of the Josephson junction. So we can um, make some Fourier transform to the states between the phase and the number states. So we can construct this kind of Josephson junction Hamiltonians by this quantization. So we can see this Hamiltonian by these e equations, so we can make some Josephson junction Hamiltonian. So, and after this, we can insert some interaction Hamiltonian after this term. So I'm gonna talk about the types of noises. Um, since we evolve in an open system, we are affected by external factors. So noise can be broadly categorized into two types. First one is systematic noise. When a pulse is shot that rotates 180 degrees, it rotates more. So if it accumulates, it may appear as random noise. And the second is stochastic noise. Noise caused by the random factors like heat generation of the resistor, or so it can make and V and I fluctuations, so additionally generated electromagnetic fields. So we can fix these noises by catching noise or engineering design required to be strong against the noise. So I will explain about some mathematical models of noise. So we can easily um, remind the block sphere representation here. So we can make some block sphere representation by here. And so we can construct the density operator by this basic block sphere representation. So we can easily find, we can construct this matrix of the density operator. And so we will explain about the block Redfield model of decoherence. These are kinds of the decoherence models. So first one is longitudinal relaxation. So um, basically the qubit states is not fixed because it's a kind of quantum dynamics, so it can make some vibration between 0 and 1 states, so excited to ground states. And there can be some pure dephasing in the by xy plane, so it makes some phase difference in the qubits. So also then we can make the transverse relaxation model of the superconducting qubits. It can cause decoherence and um, vibration phase noise in here. So we can construct this density matrix including decoherence. We can insert this term um, and this term in the density matrix. Um, we can easily find in the 0 times 0, there are exactly same with this density operator. And we gradually decreasing by this um, longitudinal relaxation in the diagonal term, because it's naturally nature wants to go to the lower states. So if we make one state, nature wants to go to the naturally zero states because it's the lower state. So this is we can we can fix in our engineering model. And also there are some pure dephasing in these anti-diagonal terms. So we can define the gamma 1 is 1 of T1 and gamma 2 by the 1 of T2 equals half of gamma 1 plus gamma phi. So we can fix this model to the um, some with about some Gaussian noises. So we can modification due to the 1 of f time noises. So when noises come together to influence something, they follow a Gaussian distribution. So interpret as Gaussian distribution of 1 of f noise, which is not longitudinal noise. So we can rewrite the density matrix this additional the Corin's function term. So um I will explain about the noise power spectral density. So noise source power spectral density is the power that the signal has at each frequency. So an correlation function is a function that measures the correlation between signals over time. So classical computer has symmetric PSD, but quantum system has not symmetric PSD. We have such these graphs in the quantum computer. So we can find this asymmetric properties in the quantum computer because we should have some symmetry in the classical computer by this function, but we can see this function is not symmetry, but we have Johnson-Nyquist noise, so it can just go up in this graph. And so um so we will explain about some microwave engineering and control. We can control this quantum qubit states by some policies. Um, so we so we can control the qubit states by the like pi policies or half pi policies. So this is the reference of my presentation, and thank you for listening my presentation.